Rewarding chapter. Okay, Chemistry 3101. We're starting chapter 8 today, which is addition reactions of alkenes. As you guys know what an alkene is, right? If you have an R group and then you have a double bond, and I'm just drawing a transalkene here, and you know that we can have a mono-substituted alkene. That's where we have one R group on our carbon-carbon double bond. We can have a di-substituted. It could be cis or trans. I'll just draw trans. We could have a tri-substituted alkene, right? We could have that. And then, of course, we could have a tetra-substituted. And something that we covered earlier on in chapter 7 was that the more substitution that you have on your double bond, the more stable it is. So we'll put here most stable. Okay, so the more substitution you have on that double bond, the more stable it is. Anyhow, with respect to addition reactions, okay, addition is the opposite of elimination. In chapter 7, we covered elimination in detail, right? Elimination, we looked at E1 and E2 reactions, but now we're not doing that. We're taking an alkene and we're going to add something to it, okay? We're going to add two groups here. It says X and Y, so you add one to each carbon of what was formerly the double bond, and we break the pi bond, right? Here, this is a pi bond, and we end up making two new sigma bonds along the way. Now, there's a whole holy host of different types of addition reactions. I'll walk through them with you. In section 8.5, we're going to cover what's called a hydrohalogenation. This is where we add a hydrogen and either chlorine, bromine, or iodine across our double bond. And I'll teach you about Markovnikov. So Markovnikov versus anti-Markovnikov addition. That's also going to come up in the section on hydration, which is where we're just adding H2O to a molecule, but you can think about it as adding a hydrogen atom and a hydroxyl group like this. You can think of a water molecule like that. The next one is hydrogenation. This is where we add H2 to a molecule, so hydrogen gas. The next one is halogenation. This is where we add either Cl2 or Br2 to our molecule. The next one is a halohydrin. This is where we add a halogen and a hydroxyl group, so a halogen and a hydroxyl group. And then we're going to look at a whole bunch of different types of dihydroxylation. We're going to look at forming cis dihydroxyl groups, or putting them on the same side of a double bond and on the opposite side. So we're going to look at what are called syn and anti addition of hydroxyl groups. Anyhow, that's some of what we're going to take a look at in this chapter. And when you think about the pi bond in an alkene, right? Again, that's the focus of this chapter. We're always going to be starting it with an alkene of some sort. So we'll just say we get an alkene like this. And then we're using the pi bond, okay? Now, how are we going to use the pi bond? Well, the pi bond is an electron pair donor, because remember, pi bonds are weaker than sigma bonds. So the pi bond can either function as a base. Here you see it functioning as a base. It's picking up the proton from this acid to make a carbocation. Or the double bond, the pi bond, can behave as a nucleophile. If you put it in the presence of a strong enough electrophile, it can attack said electrophile. And we're going to see examples of both of these in chapter 8, the pi bond functioning as a base or the pi bond functioning as a nucleophile. So where do you find alkenes in your everyday life? I don't know, the alkene section at Target maybe? Kidding. Anyhow, alkenes are all over the place in our lives. For example, if you like garlic, okay, some people really like garlic. If you like the odor of garlic, I don't know, I guess that's maybe somewhat polarizing. But anyhow, you can see that there are double bonds, right? You see alkenes in this allicin, which is responsible for the odor of garlic. Also, I'd say another polarizing odor is geraniol. Some people love the smell of geraniums, other people not so much. But geraniol is not just found in geraniums, it's found in roses, and any kind of cheap perfume. It's going to have geraniol in it. And you can see that it is an alcohol, but it also has a couple of alkenes in it here in geraniol. What else? You know the waxy coating on an apple skin, that's alpha farnesene. So you can see there's double bonds all throughout it here. You even have conjugated double bond here. What else? Cholesterol. I'm sure you've all studied cholesterol. I know that a lot of you have taken advanced biology classes. And so you would have talked about the phospholipid bilayer and how you can have cholesterol in that bilayer. And yes, cholesterol is an alcohol. You can't see the hydroxyl group. There it is. But cholesterol has a double bond in it. Alpha pinene, which is found in turpentine, can be used as a paint thinner. Limonene, if you like the smell of oranges, limonene has 2 alkenes in it. But the bottom line is that we find alkenes all over the place. I mean, we could keep going for hours, literally, of looking at drugs and naturally occurring compounds that have alkenes in them. And so cholesterol, pinene, limonene, another one would be pheromones, okay? If you know what a pheromone is, so a pheromone is some kind of, compound that's excreted by an animal that elicits some kind of response in somewhere else in another insect or animal. But you can see that this is muscular here. This is an alkene, and it's a sex pheromone of the common housefly, which is kind of cool. I already showed you farnesene on a previous slide here. But anyhow, we could go on and on. This one here of this coating moth, or sorry, codling moth, pronouncing that wrong. But anyhow, you see the alkenes are found everywhere. Also industry, okay? You guys have all watched enough of the news, I'm sure, to hear about the price of crude oil, right? So you know all about petroleum and crude oil, okay? And what are some of the compounds that we can isolate from petroleum? Would be ethylene and propylene. And you might think, well, these compounds look pretty boring to me. They're pretty small. It's true. However, it says here 70 billion pounds of propylene and 200 billion pounds of ethylene are made from cracking petroleum. So if you're going, well, what the heck am I going to do with these? It's a good question, but you can use ethylene to make a lot of different compounds. You can even make ethanol from ethylene, and propylene can be used to make a lot of compounds as well. You see ethylene glycol, polyvinyl chloride or PVC, acetic acid, right? The list goes on. And then from propylene, we get propylene glycol, acetone, et cetera, et cetera. And so alkenes are very, very important. So, we're going to focus on a lot of reactions in this chapter. And so the bottom line is when a chemist, an organic chemist especially, sees an alkene, is that person is going to say, well, I can do a lot of things with this alkene. There's a lot of different reactions because alkenes are very useful functional groups. Anyhow, hopefully I made some points there in section 8.2. But before we can start discussing alkenes, right, before we can start talking about them as a group, what's the first thing we have to do before we get into a really deep discussion on alkenes is we have to learn how to name them, right? We can't talk about them without being able to give them a proper name. Now, I have some good news. If you worked hard on, which I know you all did, on your nomenclature in chapter 4, remember we learned how to name alkanes, and I said you've got to know the 4 alkyl groups: methyl, ethyl, propyl, isopropyl, butyl, terbutyl, secbutyl, isobutyl. All those rules are still pertinent. They haven't changed. And all those alkyl groups like isopropyl, butyl, and all that stuff, those are still the same. So if you can name an alkane, my friend, you will not struggle too much with naming an alkene, because it says here that alkenes are given IUPAC names using the same procedure as alkanes, just with a couple of modifications. Look, it even says here minor, not a big change. You remember how with alkanes, I just said find the longest chain, my friend, just find it, okay? With an alkene, it's the same thing. You find the longest chain, but it has to include the carbon-carbon double bond, okay? So that is new. That is a new rule. We've got to have the longest chain, but now we're adding one thing to it. It's got to include that double bond, okay? So it's got to include the double bond. What next? Identify and name the substituents. Is it a methyl, an ethyl, a chloro, a fluoro? Assign a locant. Remember, a locant is just a TATC name for a number. In a prefix, is it 2,4-dimethyl, etc. Give the carbon-carbon double bond the lowest possible number. So that's another rule. Okay, we're going to want to give the carbon-carbon double bond, or our functional group, the lowest possible number. And if you're like, well, there's 2 carbons involved in the double bond, yes, but we only give a number to the first one. Okay, so we list the numbered substituents before the parent name in alphabetical order. Ignore prefixes except iso. Remember, we also ignore cyclo, and neo, okay? When ordering alphabetically, the carbon-carbon double bond locant is placed either just before the parent or just before the -ine suffix. I'll show you an example of this. Don't worry, I'll show you what that means exactly. So let's take a look here, and you're going to sort this out very quickly, my friends, okay? So if I asked you to name this compound, you'd say, well, it's got 5 carbons, it's a straight chain alkane, it's pentane. Okay. So if I put a double bond in it, all you do is you change the suffix from ane to ene. So now this is pentene, but remember, we wanted to give the double bond the lowest possible number. So we're going to start numbering from the right, in this case, 1, 2, 3, 4, 5. So the proper name for this compound would actually be 1-pentene. Okay, that would be the proper name. Now, if we go down to this one here, again, going by the alkane rules, the longest chain had 8 carbons, and it's an octane. And yes, that chain is still there. However, what was the rule for an alkene? If you have an alkene, you've got to find the longest chain, but it has to contain the carbon-carbon double bond. So we have 1, 2, 3, 4, 5, 6, 7, like that. So we have some kind of heptene. It's a 1-heptene because the double bond begins on carbon number 1. And then we have a 3-propyl here. So the proper name for this compound, if I can squeeze it in here, would be 3-propyl 1-heptene. Now let me just back up for 1 second. You know that rule number 5, where it says you put the locant for the double bond either before the parent name or before the ene suffix? So instead of calling the compound here 1-pentene, also, this is acceptable, you can call it pent-1-ene. So that's putting the locant just before the suffix. In here, you could call this 3-propyl hept-1-ene. Remember, we always separate a number and a letter by a dash, okay? So hept-1-ene. And again, either one is totally acceptable by IUPAC. There's nothing wrong with either of them, okay? So, I think you guys have that all figured out already, but he just gives you a couple of examples here. Let's say you had a compound like this, right? You find the longest carbon chain has 7 carbons. You number it starting from the left in this case, so that the first carbon of the double bond is going to be number 2. So this is some kind of 2-heptene, and then we have methyl groups at carbons 5 and 6. So this would be 5,5,6, 5,5,6 trimethyl 2-heptene, 2-heptene, or hept-2-ene. Either one is fine. And he said, well, if you started numbering over here because you want to give the methyl group the lowest possible number, that's not the way it works with alkenes. You want to give the double bond the lowest possible number. Don't worry about other groups. Okay? So put everything except isocycloneo in alphabetical order. Ignore prefixes, like I said. I showed you this rule already. And so if you have a double bond, if it's got the E or the Z configuration, or cis or trans, if it's E or Z, we usually put it in parentheses before the name. If it's cis or trans, then we don't do that. So you could call this compound E556 trimethyl hept-2-ene, or you could call it trans, right? Because the 2 hydrogens here, here and here, those are trans to each other. Either way is fine. So with that in mind, let's just see if we can put all that together and, just take it step by step and see if we can name a couple of alkenes. And I bet you guys have the first one figured out while I'm talking, okay? Could anybody tell me for the 8.1a, could anybody tell me how many carbons are there in the longest chain that contains the double bond? And it's not a trick question or anything. Yeah, thanks, Lauren. Yeah, there's 6, okay? Now, Lauren, I can start numbering from the left, or I can start numbering from the right. Should I start numbering from the left or the right in this case? Go with your gut on this one, right? Because either way, the double bond, it's going to be from the left in this case. Okay, let me show you why. Okay, so if I zoom in here, if I was to number here 1, 2, 3, right, then I get the methyl group at carbon 3. If I was to start numbering from the right, then I have 1, 2, 3, right? I still get a 3-hexene, but now my methyl group is going to be at carbon number 4. So I want to, right, either way the double bond gets the same number. So I go with the next rule, which is I want the methyl group to have the lowest possible number. Does that make some sense? I hope that makes some sense. Anyhow, cool. All right, awesome. So we have 1, 2, 3, 4, 5, 6. So this is going to be some kind of 3-hexene, right? Because we have 6 carbons. So this is a 3-hexene. And then we have a 3-methyl. So this is going to be 3-methyl, 3 hexene. There's only one thing that I'm missing here, and that is to label this compound as an E or a Z alkene. So if I look at the two carbons of the double bond, I have this carbon in red and this carbon in green. Would this be an E alkene or a Z alkene? Can anybody answer that? And it's not a trick. Is this E or Z? This one would be an E alkene, wouldn't it? Right? Because if you look at the carbon in red, the highest priority group is going to be the ethyl group. If you look at the carbon in green, the highest priority group is going to be the ethyl group. So this compound, you could call it two ways. You could call it E 3-methyl 3-hexene, or since they're both ethyl groups, you could call it a trans compound. So copy. I'll just change the color here. Or you could call it trans 3-methyl 3-hexene. Either one is totally fine. Okay, there's nothing wrong with either of them. All right, there we go. Let's take a look at the next one. It's a little bit heavier, isn't it? Right? There's a lot of carbons here, but I've gone ahead and already found the longest carbon chain. If you number starting here, 1, 2, 3, 4, you get the double bond on carbon 4. But if you start numbering here, 1, 2, 3, 4, you get the double bond on carbon number 4. Okay, so should I start numbering where I have the blue numbering or the red numbering? Could anybody tell me that? Would it be the red numbering or the blue numbering? It's the blue numbering, right, Hannah? That's correct. The reason why is because if I go in the blue one, I have 2 methyl groups on carbon 2, or if I go with the red one, I only have 1 methyl group, right? I want to give the substituents the lowest possible numbers. So the blue numbering is going to be correct. So I'll just remove everything there, and we'll put 1, 2, 3, 4, 5, 6, 7, 8. So let's see here. We've got a couple of ethyl groups on here, and then we've got 1, 2, 3 methyl groups. So this is some kind of 4-octene, and then we have 2 ethyl groups and 3 methyl groups. So ethyl comes before methyl, so it's going to be a 4,5 diethyl. So let me scribble this down here. It's going to be 4,5 diethyl. I'm forgetting something though, aren't I? Let me just move it over here to the right. So 4,5 diethyl. Let's see here. 2,2,7. 2,2,7 trimethyl. And then 4-octene. And if you put oct-4-ene, that's totally fine. Now, could anybody tell me, is this an E compound or a Z compound? This one. E compound or a Z compound? Yeah, it's an E compound, isn't it, right? You could say this is the biggest group over here, and this is the biggest group or the highest priority group over here. So this is an E compound. It is totally an E compound. There's no arguing that. However, could you call it cis or trans, this particular compound? Could anybody tell me that? Could you call it cis or trans in this specific case? Yeah, thanks, Lauren. Yeah, you could totally call this a trans compound. Why could you call this a trans compound? Because of the 2 ethyl groups, right? Those are identical and they're on opposite sides of the double bond. And so either one is fine. So you could call it E4,5 diethyl 2,2,7 trimethyl 4-octene, or you could call it a trans compound as well. Both are totally fine. There you go. So a little bit about alkene nomenclature. Make sure you are able to name an alkene. Okay, very important. And something that I like to do is kind of practice my nomenclature along the way. So as I'm working on, practice problems, I'll just see if I can name an alkene along the way. Just especially little ones, it's kind of good to just get in the habit of naming them quickly. So, like I told you at the very beginning of the chapter, so if you go all the way back here to 8.1, I said what we're going to look at mostly are going to be addition reactions. That's where we add something to the double bond. Well, we want to talk about the thermodynamics of this just for a second here, okay? And talk about why or when do we have conditions that favor addition and when do we have conditions that favor elimination? Because we studied elimination at length in chapter 7, and we're going to cover addition at length in chapter 8. So if you're wondering, well, if I add a halogen and a hydrogen, why don't I just get elimination again to make my double bond? Well, which side is favored, it says here, depends on the temperature at which the reaction is run. And so let's take a look at this equation, this old chestnut, which is delta G is equal to delta H minus T delta S, okay? You know that when delta G is negative, the reaction is spontaneous in the direction it's written, and when delta G is positive, it is non-spontaneous in the direction it is written. So if we think about this reaction, meaning the addition reaction, meaning going in the forward direction that it's written here, okay, we have to take two things into account. We have to take the enthalpy term into account, so that's delta H, and then we have to take the entropy term into account. Now remember, the sign of delta H can be positive or negative. The sign of delta S can be positive or negative. But remember, the sign of T is always positive, right? Temperature, because it's in Kelvin. So we have to figure out what's the sign of the enthalpy term going to be and what is the sign of the entropy term going to be. And then we can figure out which one of these reaction pathways, whether it's addition or elimination, is going to predominate. So let's start by taking a look at enthalpy. So delta H, if you think about what is happening in a addition reaction, you're breaking a pi bond, you're breaking one sigma bond. Yes, that's true, but you're forming two sigma bonds, okay? Now sigma bonds are stronger than pi bonds. So overall, that means there's going to be energy released because we're forming more stronger bonds than we're breaking. And so that means that the delta H sign for an addition reaction is going to be negative. They're going to be exothermic reactions. Now remember, when delta G is negative, it's spontaneous. So that means that addition reactions, if we're looking for a negative number, well, delta H is negative. So that means that addition reactions are actually favored in terms of enthalpy. So that's good. Okay. Now what about entropy? Well, entropy is delta S. Okay. Now let's think about that. What's happening is we're starting it with two reactants and we're only ending up with one. So if you remember back when we talked about entropy, and this was chapter 6, okay, I'll just write it down here if you need to go back and take a look, is that the entropy actually decreases in this case. So entropy has a negative sign. So now let's put all this together. Let's think about this. So if I write down my formula, delta G is equal to delta H minus T delta S. We're thinking about the reaction again in the forward direction. That's all we were talking about, right? The delta S in this direction, okay? Delta, we'll put here delta H is equal to negative and delta S is equal to negative. That's what we're talking about right now. So we've got a negative number and then we're subtracting a positive times a negative. So that's the same thing as saying a negative subtract a negative. So that means we're adding something to it overall. So when is the forward reaction going to predominate? It's all based off of what? Temperature. If the positive number is really low, that means that the enthalpy term is going to dominate and the reaction is going to be spontaneous. So that means that addition reactions are going to be favored at low temperature. If you jack this up, if you jack the temperature up super duper high, that means the entropy term is going to dominate and the delta G is going to be positive, and that means that elimination is going to be favored at high temperature. Now, I'm never going to ask you to sit down and write me like a 10-page essay on this idea, but I think you should understand the concept. And at the very least, you want to know that at low temperature, addition is going to predominate, whereas if you're at a high temperature, elimination is going to predominate. Okay, so low temperature, addition is going to predominate, but at a high temperature, elimination is going to predominate. All right, give me a thumbs up if you're with me. Is everybody with me? Like, let's say even 50% of the way on this idea. Okay, on the treatment of delta G. Okay, cool. All right, now if you're still struggling with it, what I recommend is going back here. Okay, go back to this formula here. So remember, the sign of your delta H is negative. The sign of your delta S is negative for an addition reaction, so we can cross these out. What's the product of a positive and a negative? You get a negative term. If you take a negative and you add a negative to it, okay? What does that mean? It means, sorry, if you add a positive, sugar. So the way that they write it here is, the way that I did it is easier. So let's go back here. If you take a negative and you subtract a negative from it, okay? So like that, that means it's like you're taking a negative and you're adding something to it. So if this term is small, then it means that you're going to end up with a negative number. So that means at low temperature, you end up with a negative number. If this number is high because of a high temperature, that means you're going to end up with a positive number. Okay? If you don't believe me, you can just plug some numbers into the formula, just make some numbers up, and you're going to see that you will get a negative delta G for a low temperature and a positive delta G for a high temperature. Anyhow, let's not spend any more time on that. Let's get into the addition reaction. So again, if you go all the way back to this slide here, when we were going to start looking at addition reactions, we start in section 8.5. Okay, so that's where we begin our journey into addition reaction. So it starts right here. And the first addition reaction we look at is hydrohalogenation. And hydrohalogenation reactions are the addition of a hydrogen and a halogen. Remember, the X stands for a halogen. But the only ones that we're going to look at are going to be chlorine, bromine, and iodine. Okay, there's reasons why we don't look at HF. It's because HF is not a strong acid, so it can't protonate the alkene. But anyhow, so it's the addition of a hydrogen and a halogen across a double bond. So let's take a look at what's happening at this reaction here. We've got this compound here. What would you call this compound? You'd call it trans 3-hexene. So you could call this trans 3-hexene. And then you're adding hydrogen bromide to it at low temperature. Remember, addition reactions are favored at low temperature. And if we look at the carbon in red and the carbon in blue, on the carbon in red, we added the hydrogen to it. It's not drawn, okay? This hydrogen is not drawn because this is a bond line structure, but it's implied that it's there. And there was already one there to begin with because you started it with the alkene. And now the carbon in blue, which already did have one hydrogen attached to it, that's the one that took the bromine, okay? So this is the carbon in blue. So everybody with me on that? One carbon, the carbon in red takes the hydrogen, the other one takes the halogen. That's hydrohalogenation. Now keep in mind that this alkene is symmetrical, right? There's a line of symmetry down this molecule. But what happens if you have an alkene that is asymmetrical, like this one here? You would call this 2-methyl-2-butene. So 2-methyl-2-butene. What's going to happen in that case? Because you have one carbon that has one hydrogen on it, and the other carbon has no hydrogens on it. Well, the rule that we use is this, is that the rich get richer. Okay, and what that means is the carbon that is richest in hydrogens, which is this carbon here, okay, is the carbon that's going to take the hydrogen. The other one is going to take the halogen. Take a look. Okay, so it says here that this was actually discovered by a Russian chemist by the name of Markovnikov way back in the 1800s, and he found that when you do a hydrohalogenation on an asymmetrical or an unsymmetrical alkene, that the carbon that bears the most hydrogens, okay, richest in hydrogen, is the one that takes the hydrogen from your hydrogen halide, okay, whether it's HCl, HBr, or HI, and the other carbon, the one that has the less hydrogens, takes the halogen. We call that Markovnikov addition, okay? This is what we call Markovnikov addition, is this right here. Another way to think about it, if you don't like the rich get richer way of thinking about it, you can just say whichever carbon is more substituted, meaning this one, is the one that takes the halogen. Okay, that works too. It's the same thing, but either way works. Now, what happened was Markovnikov did this reaction here. He did this hundreds and hundreds of times. maybe thousands of times, I don't know, but he did this reaction a lot. And what he found was that he got this product most of the time, but sometimes he ended up with this product where he had the halogen in the other position, okay? And that's called the anti-Markovnikov product. Because that doesn't obey the rule, the rich get richer. So that is shown right here. So you can see that this carbon is richest in hydrogens, and now it's taking the halogen. So we call that the anti-Markovnikov product. And again, he studied this for a long time, and he couldn't figure out why it was. And he had all these different theories, and people thought maybe it had something to do with the weather or the moon or something. And it turned out it had to do with the solvent that he was running the reaction in. And if the solvent was purified, he always get the Markovnikov product. Whereas if it wasn't pure, he ended with the anti-Markovnikov product. And the reason why that happens is because when you leave solvent out long enough without being purified, is it develops peroxides. So this is a peroxide. It's not hydrogen peroxide. This is an organic peroxide, right? Hydrogen peroxide would be this, right? That's H2O2. But this is just an organic peroxide. And so when it developed the peroxide, you always get the anti-Markovnikov product. So what's the take-home message is that the mechanism must be different, and that if you just use HBr, you get the Markovnikov, whereas if you put in the peroxide, you get the anti-Markovnikov product. So here's the summary, okay? Again, let's take a look. If you look at this carbon in blue, it's got no hydrogens, no H's attached. If you look at the carbon in red, it's got 2 hydrogens attached. So if we do a Markovnikov addition, the rich get richer, okay? So now this carbon has what? 1, 2, 3 hydrogens, and the other carbon takes the bromine. That's Markovnikov addition. If you put an organic peroxide in your reaction mixture, you get the anti-Markovnikov product, okay? Give me a thumbs up if you're with me between Markovnikov and anti-Markovnikov. Just the concept. The rich get richer when it's Markovnikov, no peroxides. Once you put the peroxides in, you end up with the anti-Markovnikov product. Okay, only one person follows me on this. Okay, so let's review it again. Okay, if you look at the carbon-carbon double bond, you look at both carbons carefully. The carbon in blue is attached to carbon, carbon, carbon. It has no hydrogens. If we look at the carbon in red, it has 1, 2 hydrogens, right? The other atom that's attached to is a carbon. So that means the carbon in red is richer in hydrogens. So when we're adding the HBr, the hydrogen is going to go to one of those carbons and the bromine is going to go to the other. Markovnikov addition states that the carbon that is richest in hydrogens is the one that takes the hydrogen. So it's going to take this. So now on what was the carbon in red, we're going to have 1, 2, 3 hydrogens, and the carbon in blue is the one that's going to take the bromine. Does that clear it up a little bit? Cha? Okay, hopefully. All right, anti-Markovnikov is when we have peroxide. Okay, then we get the opposite for our regioselectivity. So let's see if we can draw a product of the following reaction. So we have an unsymmetrical alkene here, so we'd call this what? 1-methylcyclopentene, rather. If I put this carbon in red and this carbon in blue, okay, where is the bromine going to go? Is the bromine going to go on the carbon in red or the carbon in blue? Could anybody tell me that? Yes, it's going to go where the carbon in red is, right? Because the rich are going to get richer. The blue carbon is the one that is richest in hydrogens, so that's going to take the hydrogen. The carbon in red is going to take the bromine. So I'm going to end up with this compound. And so I'm going to have this and this, like that. There you go. So I end up with 1-bromo, 1-methylcyclopentane. So this is going to be the Markovnikov product. So I'll just call it Mark. And then if I have the peroxides, remember, I'm going to get the anti-Markovnikov product. So now it's not the rich getting richer, it's the opposite. So if I label this carbon in red and this carbon in green, Could anybody tell me which carbon is going to take the bromine in this case? Would it be the red one or the green one? It's going to be the green. Absolutely. Here we go. So we're going to end up with this product that looks something like that. Now, in that compound, we end up with 2 stereocenters, but we're not going to worry about those. We're not going to worry about any stereochemical considerations when we're looking at Markov-Nikov and anti-Markov-Nikov addition just yet. Now, the Y for anti-Markov-Nikov, that is covered in Chapter 10. Chapter 10 for anti-Markov-Nikov. But for Markov-Nikov addition, okay, the Y is covered in this chapter. So Y, we're going to cover that. See next slide. Okay, so let's take a look at why we get Markov-Nikov addition. Well, it turns out that the mechanism of a Markov-Nikov addition, okay, so this is again Markov-Nikov addition, is a 2-step process. The first step is a proton transfer. We end up forming a carbocation, and then the next step is going to be a nucleophilic attack. So you form a carbocation, and then your nucleophile comes in and you attack. And notice that this is Markov-Nikov addition. So the rich are getting richer. If I label this carbon in blue, that's the one that's taking the hydrogen. Now, I'm going to prove it to you as to why Markov-Nikov addition occurs. If I redraw this alkene down here on the bottom of the slide, so I'll just pencil it in down here, okay? And I'll put in my HBr like this, okay? Now, let's say we got the opposite. Let's say we ended up with the hydrogen at the more substituted carbon. Then I would end up with this. Okay, I'd end up with this carbocation, and then my nucleophile could come in, right, do a nucleophilic attack, and then I'd end up with the anti-Markov-Nikov product, which would look like this. But why doesn't this happen? Okay, why does this not happen? It's because of what? It's because of the carbocation. Could anybody tell me why the carbocation in the green circle is so much more stable than the carbocation in the yellow circle? Why is it more stable? Exactly, my friends. Right? You're comparing a tertiary carbocation versus a secondary. Hello, tertiary is way more stable. And so there you go. It's going to have a lower activation energy. That's the whole answer, my friend. Okay, that's it. It says the step with the highest activation energy is the rate determining step, which is the formation of the carbocation. And so if I was to form the secondary carbocation, right, then it's going to have a much higher activation energy. That's all there is to it, my friends. Nothing more than that. It's just based off of the stability of the carbocation. What I just wrote down is right here on the slides. Okay, if you compare secondary versus tertiary, tertiary is more stable. So Markov-Nikov product is formed. Why? It's because of carbocation stability. That's it. That's the whole answer. That's the big reveal right there. Okay, give me a thumbs up if that makes some sense to you. You're like, well, yeah, that makes sense. You're going to form the most stable carbocation, and then your nucleophile comes in, and bingo, bango, bongo. Okay, so I want you to be fully aware of, I'm going to put a red star on this, okay, of the mechanism of Markov-Nikov addition of HBr, HCl, or HI across an alkene, across an unsymmetrical double bond. Okay? All right. So now that we have that in mind, this is what I was trying to sketch out before. It's nothing more than this. This is your big answer, okay? The activation energy here is significantly lower than the activation energy to make the secondary carbocation. I'm sure that all of you could have drawn this graph without any of my help whatsoever. You could have drawn this reaction coordinate diagram, which is the proper term for it. So just to clear up a couple of other concepts surrounding hydrohalogenation. So remember, let's focus on what we're talking about here. Hydrohalogenation is the addition of HCl, HBr, or HI across a double bond, which proceeds with Markov-Nikov regioselectivity. Well, let's cover some of the nuances. First of all, if you end up making a carbocation, right, your first step in this mechanism, we could practice here, is going to be the rich getting richer. So I'm going to end up with a secondary carbocation in this particular case, okay? and then my nucleophile can come in. But remember, a carbocation is trigonal, what? Planar. And so the nucleophile can come in and attack from either face. So if there's a if you form a stereo center, you're going to form a pair of enantiomers in equal amounts. Now, if it's a diastereomer, it's a little bit more complicated. But the idea is if you form enantiomers, they're going to be, you're going to end up with a racemic mixture. So we'll just say here, racemic mixture. And if you don't remember, racemic just means a 50-50 mixture of R and S. And this is just David Klein's interpretation of it, showing you, yes, your carbocation is trigonal planar, and so the nucleophile can come in and attack from the top face, the bottom face, and again, you end up with a 50-50 or a racemic mixture. Okay, that's all they're asking about there. Equal probability means racemic, right? Okay, now what about the next kind of elephant in the room? I know you guys are very astute at determining, what's going to happen when I get a carbocation, or if I have a carbocation, whether or not, I should say, a carbocation rearrangement can occur. So let's say you did the Markovnikov addition here, okay? Remember, this carbon in red has only one proton. This carbon in blue has two protons. So I'm going to add the proton to the carbon in blue, and I end up with a secondary carbocation. Now, if you look at that secondary carbocation, it can rearrange via a hydride shift to go from secondary to tertiary. And remember, I told you that if a carbocation rearrangement can occur, it will. True. So what's going to happen is it says here, carbocations rearrange the hydride shift or the methyl shift so that they can become more stable. And so you're going to end up with a rearrangement in this kind of case. And so what you're actually going to end up with is a mixture. Okay, you're not just going to get this product. You're also going to get the product if the chloride was to attack at the secondary, and you see that summarized right here. So it says here, recall, carbocations can rearrange, hydride or methyl shift. They can become more stable. When carbocation rearrangements can occur, they will occur. Now here it says the rearrangement product is going to be the major product, and that's what we're going to assume. We'll always assume that the rearrangement product is more stable, and so it's going to be the major product, okay? So with that in mind, let's try a practice problem. It says here, predict the products for each of the following reactions. In some cases, the reaction produces a new chiral center, while in other cases, no new chirality center is formed. Now, again, I know you guys are really good at identifying these. It doesn't ask us to practice the mechanism here, but what I'd like you to do is, here's our alkene. This carbon has one hydrogen. This carbon has none. So could you just try and draw this out, okay? If you haven't done it already, I recommend trying it. Try to draw the curved arrows for this reaction. Now, the way the textbook does it, or the solutions manual, is he just does this, okay? And there's nothing wrong with doing that. And then you just say, well, I'm going to end up with this, okay? Or I end up with the tertiary carbocation. There's nothing wrong with that at all. However, your instructor, this guy, what I like to do is I like to drag the electrons through the carbon that is going to pick up the hydrogen. Just kind of a bookkeeping way. Something I learned, from one of my instructors, is just drag the arrow through the carbon that is going to take the hydrogen. It just helps me keep track of things, okay? So this is going to be the carbocation that we're going to form, okay? It's not going to undergo any rearrangement whatsoever. And so now, in the next step, what's going to happen? Come on, pen. There we go. My bromide ion, which is a great nucleophile, it's a weak base, but it's a very good nucleophile, is going to come in and it's going to attack here. So could anybody answer this? And it's not me trying to fool you. For the product that we're going to get here, will there be a stereo center? Yes or no? Will there be a stereo center in the product that we're going to form? Does anybody have an idea whether we're going to form a stereo center or not? Yeah, thanks, Jenny. Absolutely. Yep. No doubt about it, right? So I'm going to draw it with a dash here and a wedge over here like that. So that's going to be one enantiomer. And then we're going to also form the other enantiomer So I'll just put the bromine over here. There we go. So, and this is going to be a racemic mixture, isn't it? There you have it. Great. All right, the next one, again, Markovnikov addition. So I'll redraw my HCl molecule. Markovnikov addition is going to look like this. I'm going to end up with this. That's the carbocation. It looks like this. Tertiary carbocation. It's not going to undergo any rearrangement whatsoever. The chloride ion is going to be my nucleophile. It's going to come in and attack the carbocation. In this case, I end up with no stereocenter. So I don't have to draw any stereocenter. We could just put here achiral. Okay, it's not, so you don't end up with a racemic mixture. And then for the last one, am I going to end up with a chiral center? You bet your Bobby socks. Okay, I'm not going to draw the mechanism for this one. You could try to draw it on your own time, but I'm going to end up with a pair of enantiomers in this case. So I'm going to end up with this compound where I have the iodine here, and I'll just copy and paste that to make my life 21% easier. So we'll delete that and just put the iodine over here. And we'll just say here, these are enantiomers, and so we'll just say racemic mixture. Racemic mixture. There you go. Give me a thumb. Is everybody with me on what Markovnikov addition is? Yeah? Okay. And then what about the curved arrows? So remember, the first one is the proton transfer. We get the most stable carbocation, and then the nucleophile comes in and attacks. All right. So now that we have that down, let's take a look at these two reactions here. It says identify reagents that you would use to achieve each of the following transformations. So we have the same starting material or substrate, and then we end up with two different products. So let's say the first one, this one here, would this be a Markovnikov addition of HBr or anti-Markovnikov? The one in A, would that be Markovnikov or anti-Markovnikov? Could anybody answer that? Are the rich getting richer or no? Does anybody have an answer to that one? Is this Markovnikov or anti-Markovnikov? 8.6a. Yeah, this is going to be a Markovnikov addition, isn't it, right? Because this carbon has two hydrogens. This carbon has none. And so this carbon now has 1, 2, 3. So this is a Markovnikov addition. So if it's a Markovnikov addition, what are the conditions going to be? Could anybody tell me what the reagent is that I would use here? Just a plain old Markovnikov addition of, what would my reagent be? HBr. There you go. That's it. So we'll just write HBr. Now you can see in the next one, we have an anti-Markovnikov addition. Anti-Markovnikov addition. And so in that case, we're going to need HBr, and we're going to need some peroxides. Look at that. There we go. All right, so that covers hydrohalogenation. This one here, I just noticed it's the wrong number. In the textbook, this is actually 8.8. It's not 8.5. This is question 8.8. So now we've solved question 8.8, then we backed up and did question 8.6. And that brings us to the section on acid catalyzed hydration. So what we're going to cover next is what happens when we add water across a double bond. And what you're going to see is that it's going to follow the same old Markovnikov regioselectivity. The rich are going to get richer, right? If we're adding H2O, which consists of a hydrogen and a hydroxyl, that's the way you can think of water if you want to, right? You see that the hydrogen goes on the carbon that was already richest in hydrogens. So now it's, sorry, that's a pentavalent carbon. Mr. Dion needs another coffee. So you end up with two hydrogens, and the other carbon is the one that takes the hydroxyl group. So the same old Markovnikov regioselectivity, and you're going to see that the mechanism gives you it's the same rationale, right? The proton is going to be added so that you end up with the most stable carbocation.